In this video, we're going to take a look at the Bellman Ford algorithm, which is one algorithm that we can use to find the shortest path starting at a source to any other node inside of our graph. The setup for this is really very similar to the other setups that we've seen so far. We're going to keep track of the number of vertices our graph has, and we're going to store our edges generally in this format here, where we have the start of the edge, the end of the edge, and then the weight of the edge itself. Bellman Ford algorithm works well with edges that have a positive or negative weight. So the primary use that we have for this is really for negative weight situations. We'll see with Dijkstra's algorithm doesn't tend to work as well with negative weights. So that's the main example of when Bellman Ford is going to be useful. With the Bellman Ford algorithm, we're generally going to follow the following process. We're going to start by setting up our distances, which we're going to start by assuming are the largest possible value. And basically, we're going to go through this process of what we would call relaxation as we go through each of the different nodes, eventually giving us the shortest or least weight paths as possible, right? So where we start off with this is we basically start off by saying that the distance to the source is equal to 0, since the distance from the source to itself is, of course, 0. From here, we're then going to iterate through for I in range of self.v. And then we're going to do for edge in self.edges. So basically, we're going to look through every single edge that we have, and we're going to extract the edge information, so the start point, the end point, as well as the weight. And then what we're going to do is we're going to take a look at that, and we're going to see if the distance to u is not max size, and the distance to u plus the weight is less than the distance to v. So essentially, we're checking to see generally the distance of this comparative to the endpoint, right? So we're taking a look at if we were to take u plus the weight, is that less than the distance to v itself, right? And if it is, then generally what we would say is we would say, well, if I is equal to self.v minus 1, we are not going to take it. We'll return a negative 1 here. Otherwise, the distance to v, we're going to update to say that it's the distance to u plus w. So you can see generally each time what we're really doing is we're just trying to find the shortest possible distance to connect together these two nodes. And then we're picking it based on that information and storing it inside of an array, right? So every single time that we go through this process, we're going to continually add on more of the distance and weight until we've created all of those different shortest paths as possible. So from here, we can simply just do a return of distance, and we're generally going to be done. So you'll see here that when we take a look at this example graph with Bellman Ford, what we can do is the following. We can run chapter 11, bellman.py, and you'll see that for each of these, it will give us the distance from that node to any other node in the graph, right? So the distance from 0 to 0 is 0. From 0 to 1, we can see the distance is 5. And if I take a look here, I see that I have an edge directly from 0 to 1 with a weight of 5, right? I can see that for if I were to go to node number 2, right, it would be a weight of 6. So I could see that if I take 0 to 1, it takes me to 5, and then I probably have one from 1 to 2 with a value of 1, right? So you can see that that would give us a weight of 6, right, as a total. So you can see that generally this is giving us the shortest path truly, right? So this one is going to be the main algorithm that we're going to use for cases where we have a negative weight potentially. In this case, the general time complexity of this is going to be O of v squared, where v, again, is the number of vertices that we have. We can see that fairly clearly right here, right? Because we loop through all the different vertices, and then we loop through all of the different edges. And because there's going to be generally a vertice for each edge in the worst case, where the graph is fully connected, we would have O of v squared as our general time complexity for this particular algorithm. So this gives us one way of finding shortest path. The second way that we're going to talk about is Dijkstra's algorithm, which we'll take a look at in the next video. Dijkstra's algorithm will generally work on a situation where we have a weighted, directed graph with non-negative edge weights. So thanks so much for watching, and I'll see you in the next video.